Hi, guys. Okay, so let's finish this chapter 5 on thermochemistry. We are going to be looking at the learning check problems from the Hess Law. And this is from the Stax book, Chemistry 2nd edition. So the problems we will cover here is 5.13 and 5.15. We are going to leave out the challenging problem 5.14 on page 267 for now. And if there's time, I'm going to make a video on that one. But for now, let's revisit the postulates of the Hess Law. So the postulates of the Hess Law, the important ones are that it's a law of summation. So the total enthalpy change of a reaction is a sum of the change in enthalpy of pathway reactions. So every reaction has some energy associated with it. So if you add up the energies of the pathway reactions, that should be equal to or somewhat similar or equal to the target reaction. So we are going to look at the balancing of the reactions based on the Hess law and calculating the heat of the target reaction, the heat of formation. Okay, so some of the rules are that when the reaction is reversed, that is when we are balancing, then the delta H sign, which is the heat of formation or the enthalpy, that sign is also reversed. If the coefficients in a balanced reaction are multiplied by an integer, then the delta H value is also multiplied by the same number. So that should be kept in mind. Next is that on the common side, the reactants or the products, the common on the reactant and the product side cancel out. They cancel out on the opposite side, but on the same side, they are added. Okay, and then when you balance in fraction, now this is just a little cheat sheet for those students who have a hard time like visualizing the fractions. So here it is, when you balance in fractions, first multiply by the number, for balance in fractions first, and then multiply by the number that is needed. So let's look at this. First of all, hydrogen plus half of oxygen is equal to water. So if you look at it here, in water, there are 2 hydrogens. So here we have 2 hydrogens. So this is balanced. But on the water side, we have 1 oxygen here. Now, for a molecular equations, normally you would add 2 or 4, to make them balance. But we bring it to the lowest, the numbers. So here we have 1 oxygen on one side. And so how can you make it 1 on the reactant side? So here we have 2 oxygens. So we need only 1 oxygen out of the 2. That is why you put half. Half of 2 is 1, and that equals to the 1 on the other side. So that's one piece. Next is look at the phosphorus. Now, phosphorus 1 and phosphorus is 1. So this is balanced. Now look at the chlorine. So we have 3 chlorines here. Now, how can you get 3 chlorines? You have 2 chlorines on this side. But instead of putting 2 and 3 like you do the molecular balancing, here we are going to say, okay, we need 3 chlorines. So if we have 6 of those chlorines on one side and then divide those by half, then it becomes 3 chlorines on this side. So that is why the reason we put 3 by 2 on this side. 3 by 2 would mean that first you have 3 times 2 is equal to 6 chlorines, okay? And then half of 6 chlorines is equal to 3 chlorines. And that is what you have here. So this is how this balances up, okay? Now let's look at the reaction in which 5.13, we are given the delta H values of 2 reactions, okay? These are called the pathway reactions. So these pathway reactions are what lead to the target reaction, which is iron plus 3 by 2 Cl2. Now 3 by 2, remember that 3 by 2 stands for 1.5. This also is written like that. So it is equal to 1.5, and that is equal to 3 by 2. So this all are the different ways of writing the same thing. So this all means 1.5. Okay, so 1.5 Cl2s is equal to, FeCl3. So here's the thing now. You are given these two reactions and you are being asked to find the delta H value of the reaction in which iron as a solid is reacting with 1.5 Cl2s to give you FeCl3, and you need to find the delta H, the heat or the enthalpy change or the heat of formation of this reaction. You are given iron reacting with chlorine gives you FeCl2, and the heat of formation of this reaction, it is an exothermic reaction, and it's negative 341.8 kilojoules. Okay, so that's one thing that is given. Next thing is given is FeCl2, that is an intermediate that is formed. As a solid, reacts with half of Cl2 as a gas, and this gives you FeCl3 and delta H, that is the heat of formation of this reaction. And again, this is the exothermic reaction. That is why the value of delta H is negative. Okay, now let's do this. Whenever something, always for the Hess law, there's another, always, let me put this in black, always use pencil because you might have to go back and forth. So always use a pencil. So you don't have to erase and all that. Okay, so let me just clear this up. Okay, now we are given, rewrite what is given and compare. Now compare with the target reaction. Compare with target reaction. Whatever is given to you, you compare that with the target reaction. So I have rewritten here iron and reacting with Cl2 giving you FeCl2. And FeCl2 reacts with half of chlorine to give you FeCl3 and the delta H value. So you compare them with the target. Now in the target reaction, what do we need? We have FeCl3 we need on the product side. So this is the FeCl3 on the product side. So this one we are going to keep as is. So this reaction, you're not changing. So keep as is. In other words, do not reverse. So that's one piece. Next is you are given iron. You need iron on the product reactant side and 3/2 Cl2, 1.5 Cl2 on the reactant side. So we have iron here and then Cl2, and we will balance out, we will bring it the 3/2. Okay. All right. So we need these. So this is again because these are on the iron and the chlorines are on the reactant side in this reaction. So therefore we are also going to keep this also as is. In other words, we won't reverse it. Okay, now you rewrite the same thing. And another thing that we need is this 3/2. How can you make this 3/2? So normal tendency is to multiply by 3, but hold on to it. Look at this. Remember, that is why I wrote this so that it's clear. Sometimes that's where the confusions are. 3/2 also means 1.5. 1.5. Okay, so 3/2 and 1.5 is the same. So here we rewrite this after we have decided which ones are we keeping as is. So now you are taking iron plus Cl2. Remember that this guy is actually 1. So don't forget that. And then you have half. So then what does this become? So now let's just add these two together because now we are keeping it the same. So you add these, we are not reversing anything. So these signs remain as they are of the delta H value. So we see that FeCl2 and FeCl2 are on the opposite side, but they're common. So cancel out. Okay. Next is we are going to have FeCl3, which is what we want, FeCl3. And this is as a solid. And we have iron, which is as a solid. And then 1.5 Cl2 is 3/2 Cl2. Okay, as a gas. And this is giving you FeCl3. Now, negative 341.8 and negative 57.7 kilojoules. So minus is added together. So what do you get here? So when you add the two signs for the delta H, we get negative 399.5 kilojoules per mole. And the sign is obviously when you add, but the sign is of a bit number, so a negative. So that's your answer for this question. Okay. Next is calculate the delta H for the process in which nitrogen is given, oxygen is given, and nitrogen dioxide is formed, and you need to find the value of delta H. So this is your target reaction. It's very important you write down the target reaction because it allows you to compare with the given. Now, we are given nitrogen. So this nitrogen and this nitrogen are matching. That is, they are both on the reactant side. So we're good with that. We'll keep it as it is. We need 2 oxygens. So it doesn't matter, but at least oxygen is on the reactant side. This oxygen is also on the reactant side. So we are keeping as is. Now we don't need nitrous oxide. We do not need that. But we need nitrogen dioxide. So we are going to keep this as is also. So nitrogen dioxide is on the product side in the target reaction and the given reaction. So keep as is this one, and here also keep as is. Okay, so the rest of it is going to be canceled. So after you do that, here, since we are not reversing, we can just continue here. So now keep in mind that on the, let me just do this here, keep as is. Now here we are given the 2 NO, and in this other reaction, we are given only 1 NO. So we need to multiply that by 2. Next is the 2 nitrogen dioxide is what is needed in the product side. And here we are only given in the given reactions only 1. So anyways, this whole thing is going to be multiplied by 2. Okay, so this is 2. And then 2 times half, and then here 2. So remember that 2 times half becomes 1. So this is 1 O2 now. Okay, so this is 1 O2 as a gas. So I'm not going to just, I'm not going to, otherwise it will be redundant, but this means 1. So now 2 NO and 2 NO cancel out, and 2 by 2 is equal to 1. Now remember that this is 1, this is 1 oxygen, and this number right here is also 1. So 1 and 1 becomes 2 O2 as a gas. Okay, and here you bring down the nitrogen as a gas as it is, plus 2 O2 as a gas gives you 2 NO2 as a gas. Okay, now here's something else. This also will be multiplied by 2 because the rest of it was all by 2. So when we do that, let's get this number. Okay, so 57.06 times 2 is negative 114.12. And when you basically add, but minus minus becomes plus. So plus sign, plus with a minus sign is equal to a minus sign. So minus minus is, the plus and minus is minus, and the sign will be of a bigger number. So here, this comes out to be negative, this comes out to be 66, a positive 66.38. And then if you round it up, this becomes 66.4 kilojoules. Okay. So that is the answer for this reaction, where the value of delta H is kilojoules per mole. Sorry, it can't be per mole. It's for it because actually you are producing 2 nitrogen dioxide, so it's just 1 mole. No, it's for 2 nitrogen dioxides. It is 66.4. Okay, so this is the answer. All right. Now let's look at 5.15. Now 5.15 on page 69. This relates to another way of calculating the delta H for the reaction is, well, one of them is the one that you had been doing. If you are given just not the actual pathways, not by this whole process of looking at the individual reactions, if you are just given the delta H value or the enthalpy of one reaction, enthalpy of second reaction, enthalpy of third reaction, and so forth, you add up. Remember, it's a law of summation. Hess law is that. So you add up all this and you will get the, you will get the total, the target reactions for the total, for all these reactions. Okay, and that is your target reaction. So that is one way of doing it. Another way of doing it, you take the total heat of the reactions is the sum total of the number of moles times the heat of formation of the products minus the sum total of the heat of formation, minus the total of the moles on the reactant side times the heat of formation of the reactants. Okay, so that is if you multiply these moles by the heat of formations of the products and the reactants, and you subtract them, then you get the heat of the reaction. So the first one is just adding, so we can just leave that, but let's look at the second one. Calculate the heat of the combustion for 1 mole of methanol. Now here's very important. We are talking about a reaction, which is a combustion reaction. Combustion means that the reaction is actually with oxygen, burning with oxygen. So 1 mole of methanol is burning in oxygen to give carbon dioxide and water. So always write the combustion reaction and balance that equation. It's very important. So let's do that. So here you have C2H5OH plus oxygen gives you carbon dioxide plus H2O plus a lot of heat is evolved. Okay, now that's the amount of heat that they're asking to find. Okay, so here in this case, methanol as a liquid reacting with oxygen as a gas gives carbon dioxide as a gas, and water, I'm assuming, is in this case is given as liquid here. Okay, liquid. Okay, so here is, in this scenario, always first of all balancing. So first carbon, always first carbon, second hydrogen, and then the third is oxygen. And if oxygen is odd number on either side, on one side, then multiply all other entities, or the rest of the entities, other entities by 2. Okay, and then it will balance out. So here, so we have 2 carbons here, we have 1 carbon here, so you put 2 here. So that balances the carbon. Let's look at hydrogen now. We have 5 plus 1, 6. 6 hydrogens on one side, and we have only 2 here. So if you put 3, this becomes 6 hydrogen. So hydrogen is also balanced. Now let's look at oxygen. So we have 1 oxygen on this side, and we have 2 oxygens on this side, and we have 2 plus 2 times 2, 4 oxygens on this side, and we have 3 oxygens on this side. So this total becomes 7 oxygens here, and we have 3 oxygens this side. So this is like, we need to balance it. Okay, so let's do that. Okay, let's look at this balancing. So right now we have 4 carbons, and if we multiply the whole thing by 2, we multiply the whole thing by 2, except the oxygens on the right-hand side. So if you put this 2 here, this makes it 4 carbons, and 5 plus 1, 6. 6 times 2 is 12 hydrogens, and then 2 oxygens here, and then leave this oxygen right now. Don't do this, don't touch this. And then take this 2 times 2 multiplied by 2. So this 2 times this 2 becomes 4 carbons. So I'll just erase this one now. So 4 carbons here. And then 4 2s are 8 oxygens, and then 2 multiplied by 3. So that becomes 6 hydrogens. 6 times 2 is 12 hydrogens, and we have 6 oxygens. Okay, so now let's look at. So we have 4 carbons and 4 carbons balanced. We have 12 hydrogens and 12 hydrogens balanced, and a total, we have 8 plus 6 is equal to 14 oxygens, okay? 14 oxygens. Now, we already have 2 oxygens here. 2 oxygens are here. And so there are 2 also here. So total of 4. So if you have, if you put 6 2s are 12. If you put 6 here, so this becomes 12 oxygen plus, so this becomes 14 oxygens. Okay, so that balances the oxygens also, 14 oxygens on both the sides. So this is your balanced equation. All right, now we are looking at the, because these moles, as I said, are important. We are going to bring these moles in these, so you're going to bring in, sorry, this one is, how do I do this? Okay, so we will be using this mold, this mold, this one, and this one. Okay, now let's do this. So for this reaction, we need to get this. So we are given, so this is going to be given to you on the test, so you don't have to memorize this, but you will be given these values, the delta H value for water, the heat of formation for carbon dioxide, and for the heat formation of this reaction, which is the combustion reaction. So let's do this. Delta H F, one second, let me just double check one thing. That is the heat of formation of water and carbon dioxide is given minus 278. Oh, okay. Because this is not for the reaction. That's a little mistake here. This is not the reaction. This is for the C2, that's the ethyl alcohol, C2H5OH, the heat of formation of ethyl alcohol in the liquid form. It's very important you get the, get these, the states. That's important. Okay, so negative 278 for the heat of formation for ethanol, and for the water in its liquid state is negative 286 kilojoules per mole, and for carbon dioxide in a gaseous state is negative 394 kilojoules per mole. Okay, now delta H. For this reaction, the standard heat of formation for this reaction is equal to the sum total of the number of moles of the products times the heat of formation of all the products, of the products, the standard heat of formation of the products, minus the heat of, minus the sum total of the number of moles of the reactants times the heat of the formation, the standard heat of formation of the reactants. Okay, so the product is C2H5OH. So here we are looking at for C2H5OH. The products are the carbon dioxide and water. My mistake here. The reaction is carbon dioxide and water, and the product is, the products are carbon dioxide and water will be here. Sorry about that. CO2 and water. So all this has to be combined. This is one thing. And the reactants was for C2H5OH and carbon dioxide. So here is for C2H5OH and O2. Sorry, not carbon dioxide, but O2. All right. All right. Now let's set this up. Okay, so you set up this problem. So for the CO2, which is the product, the number of moles times the delta H value for the CO2, add, because it's a summation. This sign is for adding up. These are the summation, so that relates to these, okay? And then, so we add the products on one side, the number of moles for the water times the delta H value for the water, and then you're going to subtract from the number of moles of the methanol times the delta H value of methanol, plus the number of moles of oxygen times the delta H value for the oxygen. So let's put in the numbers now. So here we have from this equation 4 moles of carbon dioxide. 4 moles of carbon dioxide times the delta H value, which is negative 394 kilojoules per mole. Negative 394 kilojoules per mole. That's for carbon dioxide. So this is one piece. Plus, for water in the liquid form, we have negative 286. Negative 286 times 6. So 6 of H2O times negative 286 kilojoules per mole. Okay. So these are added, and then you subtract from the reactant side. The number of moles of C2H5OH is 2. So 2 C2H5OH, that's ethanol, times the value of ethanol given is negative 278 kilojoules per mole. Negative 278 kilojoules per mole. Okay, plus the number of moles of oxygen. So here we have 6 oxygens. So 6 oxygens times, and then this is 6 oxygens times, for the oxygen, yes, it would be 0 kilojoules per mole. So for O2, it's that for diatomic molecules. And now you are going to bring in these numbers. Okay, guys, sorry, when I was doing the calculations, I realized that I had complicated a little bit. Like in other words, when I was doing these balancing, I could have simplified it. Okay, so the more simpler version of this is this one. So if you just take this thing, the more simpler way of multiplying, of balancing this would be 1 mole of methanol is reacting with 3 moles of oxygen to give you 2 moles of carbon dioxide and 3 moles of water and heat. Okay, so that's one thing. So if you use this balanced equation, in that case, then you take the number of moles of carbon dioxide. So 2 moles of carbon dioxide, when they multiply by the given value of the delta H for carbon dioxide, the heat of formation, that is 394 kilojoules per mole. Then the moles of carbon dioxide, let me use another pen, then the moles of carbon dioxide and the moles cancel out. Okay, and you're just left with kilojoules. Add that to 3 moles of water times the negative 286 kilojoules per mole, that's the delta H value, and then you cancel these moles out. Okay, so now when you multiply these two, the 2 times the 394, then you get negative 288. So you have to carry over that sign. And here, when 3 times 286, then you get negative 858. And then minus and minus is plus, but the sign is of a big number. So that is why your actual answer here becomes this is on the product side, and product side is giving you negative 1646 kilojoules of heat. Okay, next is you have 1 mole of ethanol and times the given value of the heat of formation of ethanol, and you add that to the 3 moles of oxygen times the delta H value, although it's not given, but it is understood that the delta H value for the heat of formation for oxygen is equal to 0. Okay, so that's what we have in the next line. So when you do this, obviously this whole thing is going to become 0. This zeroes out, so that's 0 kilojoules. And you are given for the ethanol is when you multiply, well, obviously 1, that's negative 278. So on the reactant side, you have negative 278, okay? Now, this whole thing has to be subtracted. So minus is plus, but since you're subtracting, so in the end, it just comes out to be total subtraction. So when you subtract 278 from 1646, you get 13 0.68, and the sign is of the big number, which is, you know, that. So that is your actual final answer. The delta H, standard heat of formation for this whole reaction is this. Okay, so this finishes this chapter, and if you have any questions, you can always ask, but the main thing is practice. Okay, thank you. Bye-bye.